Good morning, everyone. I hate that I'm not going to be able to be in our final session together. I have been selected to participate in some of our accreditation meetings that are being held today, and I did not know this until late Friday evening. So I'm going to record this lecture and act like y'all are all in here with me. If you have any questions, be sure and send me an email. So chapter 21 is about nuclear chemistry, and nuclear chemistry is a little bit different than the chemistry that we have talked about in the past. And so far this whole semester we've really been focused on the atom as a whole, and with chapter 21 what we are looking at really is now what is happening in the nucleus. So remember that a nucleus of an atom has protons and neutrons. And a lot of times the number of protons can be equal to the number of neutrons. But sometimes an atom will have a different number of neutrons that it has acquired. And this is why on the periodic table, when we look at our atomic weights, those are averages. So what we're averaging is the weights of the different isotopes. So those are the ones that have different neutrons. So within the nucleus of an atom, we have protons, which remember I abbreviated with the P superscript plus, and neutrons, and we abbreviated those with the N and the 0 to indicate that they don't have a charge. So remember that our protons, or the number of protons, is equal to the atomic number, which is what gives our elements their characteristics and how they are arranged on the periodic table. The number of neutrons, or when we look at neutrons in general, they add mass to the atom because they don't carry a charge. So they can add mass to an atom. So for instance, if we had carbon 12, and we remember use carbon 12 as kind of our standard or our model, if we have carbon 12, what that means is that it has 6 protons and 6 neutrons. Okay. But we can also have carbon 13, which still has 6 protons because it's carbon, but it has 7 neutrons. And we can even have carbon 14, which has 6 protons but 8 neutrons. And when we look at our mass of carbon on the periodic table, we know that it is 12.01. And the reason why it's not exactly 12 is because we have some of these isotopes, not very many. The atomic mass is closest to 12, which tells us that the majority of our carbon atoms are carbon 12 with 6 protons and 6 neutrons, but that we do have some that are carbon 13 and carbon 14. Well, carbon 14 is very unstable. There's not a lot to hold on to those additional neutrons, and so it is radioactive. It is going to give off some of those neutrons so that it can go back to either carbon 13 or carbon 12. So carbon 14 is unstable. It can't stay in that form. It can't stay in that situation with 6 protons and 8 neutrons for a very long time. And so it will degrade or decay, giving off some neutrons and putting it back down to carbon 12. So when we look at our nuclear equations, or we look at what is happening in the nucleus, we can use these nuclear equations. And the nuclear equations are taking a look at what is happening just within the nucleus. We're not concerned about what's happening anywhere else. We're looking at specifically what is happening in the nucleus. So I've scanned in your cheat sheets for this unit, and you'll want to have these cheat sheets handy when you are working on your assignments and labs for this chapter, because it's going to help you understand what is happening in each one of these forms of decay. So the first thing that we look at in our, or on our cheat sheet, is atomic notation. So referring to your cheat sheet, you'll notice the very first thing is atomic notation. And you see something that looks like this. This is how we are going to notate what is happening within the atomic nucleus. So the symbol represents, or the SY here represents the atom symbol. The Z is equal to its atomic number, and A is equal to its mass number, which is protons plus neutrons. So carbon 12 would then be written like this. So I've got my symbol C for carbon, its atomic number is 6, and I add the 6 protons and the 6 neutrons to get a mass number, or A, of 12. And then carbon 13 would be written like this, and carbon 14 like this. Notice that my symbol and my Z, my atomic number, don't change. The only thing that's changing here is A, my mass number, because my number of neutrons is changing. Carbon 12 has 6 neutrons, carbon 13 has 7, and carbon 14 has 8. Okay, so that's going to be how we are going to keep up with what is happening in these different nuclear reactions. And so we set these up into nuclear equations. Okay, and a nuclear equation is showing what is happening in the radioactive decay. So a nuclear equation shows what happens in the nucleus during radioactive decay. Because we don't really care what's happening outside of the nucleus. We want to see what is going on within the nucleus. That's where our radioactive particles are going to come from. Okay. So, looking at a nuclear equation, we can see what we start with, what we end up with, and then what particles are going to be released. So if you look on your cheat sheet, again on the first page, you will see the different types of nuclear particles. We have alpha particles, which are the equivalent of a helium nucleus. Okay, and so you see that's also written in atomic notation. We have the symbol of helium, He. We have the Z, the atomic number of helium, which is 2, and then our mass number is 4, because helium has 2 protons and 2 neutrons. Okay, so that's an alpha particle. And we say that nuclei that decay through the release of alpha particles, they go through what we call alpha decay. And so here is an example. So this is an example of alpha decay, and I have examples of each one of these going through the next 2 pages of your cheat sheet. So if you look at the top of page 2, you'll see an alpha particle emission. Okay, and I've shown you how we're going to balance each of these. So when we balance nuclear equations, we do the same thing as if we were balancing a real chemical equation, in that we have to have the same number of protons and neutrons on both sides of the air. So over on our left side, what we're starting with, uranium-238. So on this side, we have 92 protons because uranium is element 92. So we have 92 protons, and we have a mass number of 238. Okay, and to get our number of neutrons, we say 238 minus 92. And 238 minus 92 is 146. So we have 146 neutrons on the left side of the equation. So now we look at what we have on the right side of the equation. Okay, we have 90 protons in thorium and 2 protons for helium. So if we add those up, we have 92 protons. Okay, in thorium, we subtract here, we have 144 neutrons plus the plus the 2 neutrons in helium, and we have 146 neutrons. So we say 234 minus 90 gives us 144, and 4 minus 2 gives us 2. So 144 plus 2, we have 146 neutrons. So we have 92 protons on the left and 92 protons on the right. We have 146 neutrons on the left and 146 neutrons on the right. Okay. So what we've done is we have taken uranium-238 and it has decayed. It has released an alpha particle and left us with thorium-234. So this is an example of alpha decay. Okay? And I just wanted to show you how your protons and your neutrons have to be equal on both sides of the equation. You don't have to subtract these out every time. Okay. I wanted to do it in that instance so I could show you, but if you look at the example that I gave you on your cheat sheet, you will see this. We have radium-226, and it's going to give off some particle, or I'm sorry, it's going to give off an alpha particle to lead to some other element. Okay, so this is an example of radioactive decay. You're going to have problems that are very similar to this, okay? And what you're going to see is what you start with, which is your radium-226. It decays by alpha emission, which means it's going to release that helium. And we have to figure out what is this element, okay? And we're going to do that by subtracting. So in order to get my A, I'm going to say 226 minus 4, which is going to give me 222. And in order to get my Z, I'm going to say 88 minus 2, which gives me 86. So now I know that my unknown that I'm looking for here, sorry, I put an H there and I meant to put an X. So our unknown that we are looking for has an A of 222 and a Z of 86. So now I can go to my periodic table and find element 86, which is radon, and then I plug in its symbol. Okay, so we won't know what element is here until we do the math, until we figure out how many protons are we looking for here. In this case, it was 86, and when I go to my periodic table, I find that element 86 is radon. Okay, so the radioactive decay, or these nuclear equations, we're going to look at what we have to begin with, which is going to be on the left side of the equation, and then we're going to look at what we're left with after some type of decay. So if it undergoes alpha decay, then we know that that results in a helium particle that's going to be emitted from the nucleus, and we have to figure out what's left. And in this case, it was radon-222. Notice that there are no states of matter here. We're not concerned with any compounds. We are strictly concerned with what is happening inside the nucleus. Okay. Now, the types of decay, if you go back to your first page on the cheat sheet, you'll see the rest of your nuclear particles. Okay. We have beta radiation or beta decay, which consists of streams of beta particles, which are essentially high-speed electrons. So beta particles are shown in atomic notation with an A of 0 and a Z of -1 and the symbol of E to understand that that is beta decay or beta emission. That is an electron. Okay. And when we look at beta particle emission, and there's an example of this on the second page of your cheat sheet, we have radium-228, and it is undergoing beta decay. So you'll see the beta symbol there, okay? And when we look at what we have left, you have to pay attention to your signs, okay? Notice that for our beta particle, our A is 0. So whatever A you start with is going to be the A you end up with. So that I just brought the 228 over, all right? But look over here. On the left side of my nuclear equation, I have 88 protons. And over here on my right side, at this point, I have essentially a -1 proton. So I have to add 89 protons to end up with 88. That's why my daughter, what we call a daughter nuclide here, has 89, because 89 minus 1 is equal to 88. So anytime you have a beta particle, okay, then your proton number, your Z, is going to have to increase. Okay, so your Z has to increase. If we look at another one of these, we have iodine-131, and it decays by beta decay into xenon-131. Notice my Z here is higher because I have to say 54 minus 1 gives me 53. So I have 53 protons on this side and 53 protons on the left side. Notice that, again, my A did not change because in a beta decay, I'm not getting rid of any neutrons. And so my 131 stays the same on both sides. Okay. Now, your book gives you a little bit of information here at the bottom of page 912. It says, just because an electron is emitted from a nucleus in beta decay, we should not think that the nucleus is composed of these particles any more than we consider a match to be composed of sparks simply because it gives them off when struck. The beta particle electron comes into being only when the nucleus undergoes a nuclear reaction. Furthermore, the speed of the beta particle is sufficiently high that it does not end up in the orbital of the decaying atom. So what that means in plain English is that this beta particle, okay, that has the same charge as an electron, and we essentially refer to as an electron, doesn't come from the nucleus. It's not found in the nucleus. It is created as a result of radioactivity. Okay, so it doesn't exist until the radioactive element undergoes beta decay. And it doesn't stick around. It doesn't become part of the electrons of that. It is essentially just shot off into space. Okay, so it doesn't become captured by the orbital of any of these atoms, and it doesn't exist in the nucleus ahead of time. It is created strictly through radioactive decay. So the third type that you have is positron emission. Okay, and a positron is structurally very similar to a beta particle, but it is positively charged. So it has essentially the same mass of an electron, but it has a positive charge. And so you'll notice that the notation for a positron is very similar to that of the beta particle, except instead of -1, we have a positive 1. Okay. And this is still positron emission. So we're going to find this on the right side of the equation. And essentially this comes from the fact that a proton can decay into a neutron and this positron. If you look at the top of the 3rd page of your cheat sheet, you'll see positron particle emission, that the proton decays into a neutron and this positron. And so you see your example there that we have. We have sodium 22. And it decays into neon 22 through positron emission. Okay, notice it's a +1 now. So our Z for whatever element that is going to end up on the right side here, we have to go down. We have to subtract. So we have 11 protons here, and we have 10 plus 1, 11 protons over on the right side. Okay, just remember that this bottom number, this is Z, this is your number of protons. So 10 plus 1 gives me 11 on the right, and I already have 11 on the left. Okay. We can also have gamma radiation. Okay, gamma radiation does not result in the release of particles. So when you look at the symbol for gamma radiation, you'll notice a 0 for A and a 0 for Z, because it's not a particle. Okay, so gamma radiation is not a particle. It is electromagnetic radiation of very short wavelength. Remember, it showed up on our electromagnetic spectrum that we looked at back in chapter 6, that gamma rays are a form of radiation just like microwaves or radio waves. So they don't result in the release of any type of particle. So when you look at a situation with gamma radiation, you may just have something that looks like this. Where we see that we've given off gamma rays, but our parent that we started with, our parent nuclide we started with, is the same as our daughter nuclide. I'm using these terms, but I haven't actually written them down yet, so let me write these here. So the parent nuclide is what we start with, and the daughter nuclide is what we end up with after some type of radiation. So in this example, because we're giving off gamma rays, the daughter nuclide is the same as the parent nuclide. But a lot of times, gamma radiation is paired with some other type of radiation. Like in your cheat sheet on page 2, I've given you the example with uranium-233. That it decays by both gamma and alpha radiation. So in the decay of uranium-233, it releases an alpha particle, but it also releases gamma radiation. But you'll see my note there, gamma rays have no effect on the nuclear reaction. And what I mean by that is they're not a particle. So they don't figure into the math of working out our nuclear equation. We can also have just a neutron that's released, and you see how that's written in notation, or a proton that's released, and we use the the hydrogen atom to represent a proton. So we can have a neutron that is released or a proton that is released, and that's the notation for those. We can also have kind of a weird one called electron capture. Now, electron capture is the only one that's going to show up on the left side of the equation. Okay, and this is going to only occur in very large, unstable nuclides. And so the example I have for you on your cheat sheet on the 3rd page looks like this. Okay, notice that my electron, it has the same notation as the beta particle, because remember, beta particle is an electron. So it has the same notation, but it's on the left side of the equation. That's why we call it capture, because the nucleus is actually capturing or taking an electron. So in electron capture, the particle is going to be on the left. Okay. So your particle is going to be on the left. Okay, right here. Not on the right like all the others that we've seen. And so our A is going to stay the same. And then we'll say 82 minus 1 gives us 81 protons, and we see that that is 1,000. Okay. So if we look at the top of page 914, we see a couple of practice equations there. This is sample exercise 21.2. It says write a nuclear equation for mercury 201 undergoing electron capture. So we're going to start out with mercury 201. I'm going to go to my periodic table and find my atomic number for mercury, which is 80. So I'm going to write this in my standard atomic notation. It is an electron capture. So I know that that's going to have to be on the left side of the equation. So I'm going to write my notation for an electron, and I'm going to figure out what my daughter nuclide is. 201 plus 0 is going to stay 201. So A stays 201. Then I'm going to say 80 minus 1 gives me 79. So my number of protons, or my Z, atomic number, is 79. So I go to the periodic table and I find that that is gold. Okay. So here's my parent nuclide, here's my electron capture, and here is my daughter nuclide that I ended up with. Okay. It also asks us to identify thorium-231 decaying to protactinium-231. Okay, and that is Pa-231. So they tell me I have thorium-231. And it is decaying to protactinium-231. And I have to figure out what is it decaying to. Okay, so what is it decaying to? Well, the only thing that has changed here is my Z. My A has remained the same. Okay, so what I'm decaying to, I'm going to have just the Z that is changing. And how do I get from 91 to 90? I subtract 1. So then this is going to have to be a beta particle, because my top number stays the same, and 91 minus 1 gives me 90. So those are examples of the nuclear equations. And you have a practice set of problems that you'll work on for those. Okay, just remember, if you have any questions, to be sure and send me an email, okay, or a text. This was the first half of the lecture. I'm going to charge up my tablet that I use. My little Mimeo tablet is dead, so I'm going to charge that up, and then I will record the second part of the lecture.